for coming. To see you in the community, for those of you who don't know, and I think we've had enough of these, but pretty much everybody knows by now, is a series of programs sponsored by TSJC, the Trinidad Community Foundation, the Trinidad and Los Angeles County Chamber of Commerce, and of course CU Boulder's outreach office. One of the things I want to tell you also is that every dollar we make on these programs stays in our community. They all the money goes to local nonprofits. And tonight's proceeds are going to go to the Trinidad Carnegie Public Library. And I'm pleased to announce that over the course of the 2 years, we've raised more than $2,000 for some very deserving, very appreciative nonprofits in our community. As far as I know, as of today, there is no program for April. In March, May 10th to be exact, we're going to have the CU Moving Company dance troupe coming. They came last May, and for those of you who didn't see them, got another chance to see them. For those of you who did and enjoyed them, come back and see them. Another thing we're working on is in either May or June, we are trying to put together a tennis workshop or a tennis clinic with CU, and they're going to send down their women's tennis team coach, and it's going to be a free clinic for adults and kids and tots, and possibly some of the women's tennis team members will come down and help as well. So, but tonight we have here with us Dr. Andrew Slater, who is a research scientist with the National Snow and Ice Data Center at CU Boulder. As a scientist for the center, Dr. Slater specializes in land surface and hydrologic modeling of snow, frozen ground, and permafrost in the Arctic. Last year, he participated in the SNOWNet project in northern Alaska, sampling snow depth and water content to help improve models of climate change in the Arctic. Dr. Slater has been on several other expeditions, has collaborated on research projects, has co-authored numerous, and I mean numerous, publications in his field. He is featured in a new online resource for information about climate change in Colorado. And I think everybody got a bookmark tonight, and that website address, learn more about climate.colorado.edu, is a site that pairs some of the world's leading climate scientists with everyday Colorado citizens who are witnessing climate change or are working towards solutions in their communities. So please join me in welcoming Dr. Slater and enjoy his presentation, Permafrost and Snow, Here and There, Now and Then. Thank you.
Thanks very much. Can people hear me? Is this mic working? Maybe not.
No.
Okay, well, I'll just use this one then. That's fine. So, yes, as Debbie said, I'm at the National Snow and Ice Data Center, which is part of CU. The Snow and Ice Data Center primarily is involved in distributing data to researchers, to operations like the Weather Service, to industry, and to private citizens. However, there's a small number of us that are there just purely for research purposes, and I'm one of them. So, I think the microphone's working now, right? Yep. Okay, so as was mentioned, CU Outreach has set up this system for learn more about climate change in Colorado. Climate change is something that pretty much is inevitable, and it's good to have people that are informed about it. There's some interesting material on this website, some interesting videos, and I recommend that you check it out. So this evening, I'm going to go on a little story. And my story is about permafrost and snow and the fact that the world is changing. We can see that in various forms, sea ice, glaciers, so forth. And then I'm going to talk about permafrost. And the reason I'm going to do that is because that's what I do. I'm going to tell you what it is, where it is, how it formed, what we've seen in terms of changes, what could happen in the future, and then why do you care? I mean, it's way up there in the Arctic. Who cares down here? So I'm going to go through that, and then the last thing I'm going to go through is a little bit about snow in the west. Ooh, getting some feedback. A little bit about snow in the west, and I don't specifically cover all of that in my research. I work more with the National Weather Service for short-term weather forecasting when I do things down in the lower 48, but I thought it would be of some interest to folks here. Okay, to start off with, this is a plot of global temperature. It's the average temperature over the entire globe, and what I'm showing here is the temperature anomaly from the period 1950 to the average of the period 1950 to 1980. That's mostly a detail. The thing that you see here is, well, you see some large interannual variability, you see some decadal variability, but then the one thing that everyone sees is this big upward trend. This is measured by instruments on the land, thermometers, just as you're all familiar with. There's over 1,200 thermometers that go into this, and this particular plot is made by NASA GIS. There's about 3-4 other institutions that make a similar product. They do it all independently, and they all come up with pretty much the same answer. What it shows is that from the period 1950 to 1980, the average through that, the temperature across the entire globe has risen about 0.7 degrees Celsius, not Fahrenheit, Celsius. It's about 1.8 Fahrenheit per Celsius. This plot is interesting, but it hides a lot as well. And what it hides is where the temperature has been changing an awful lot. If you look at this, this is a map of the world, and what we have is the last 4 years of temperature. So last 5 years, 2005, 2009 inclusive. That compared to that same average period, 1951 to 1980. And the thing that immediately hits you pretty much is that all the warming we see is up here, way up in the high latitudes. There's a little bit of cooling here, a little bit of warming here in the West Antarctic ice sheet, which causes people a lot of concern. But the main thing is that it's the northern hemisphere and the high latitudes. And if we take a zonal mean, so at each latitude band we take an average of what the temperature change has been, and we plot that out, we can see that, well, in the southern hemisphere, not too much. There's 0.4 degrees Celsius increase, but not a huge amount, and part of the reason is that, well, a lot of that's ocean. But then as we go further north, we see this incredible increase in temperature. So what does that mean? What are some of the causes and effects of that? And that's what we're going to have a bit of a look at. Now, one thing that is really obvious is the sea ice. Sea ice in the northern hemisphere, in the Arctic Ocean, as opposed to the southern hemisphere. This is the September average sea ice extent in the northern hemisphere. September is the month in which the sea ice hits its minimum. And what you see is a pretty serious downward trend. This plot down here, it's for January. Both of them are from 1979 onwards, and this one is 1979 to 2010, so very recent data. And the reason I put this in here is to say that, well, March is actually the month with the maximum sea ice extent, but we haven't got this year's March data, so I used January instead. And what it shows is that both in the minimum and the maximum, there is a serious decline in the extent of sea ice. So that's where sea ice is. Now, we've seen that there's some good interannual variability, and then in 2007, things went nuts. I mean, we've never seen a plunge like that to such a low extent. The centre, we were all freaking out, going, oh my God, what's happening? Is it Armageddon or the apocalypse, whatever? It was quite a dramatic drop. And the thing to note about it is that while it went down that far, and a lot of people have said, oh, it's all okay, it's recovering. Well, it's recovering back up to the declining trend. But what I want to show you is that it hasn't actually recovered. The plots on this side, what you have in the green colour here is the old multi-year ice. That's the stuff that's been around for a long time. It's very thick. As opposed to the second-year ice in the blue and the first-year ice in purple. And so what happened is, in 2007, when the place fried, we lost a lot of multi-year ice, and actually we lost a huge amount of ice, and lost a lot of that multi-year ice, and then we can see that we've kept losing that multi-year ice. And the thing about that, why that's important, is first-year ice and second-year ice, it's a lot more vulnerable to getting fried, in simple terms. That means that the sea ice now, we only have a tiny little bit of the old thick ice. And that's why you've got people saying that, well, who knows, we might have an ice-free Arctic in the next 20 years. It's hard to tell from this, but when you start looking at this, you're thinking, ooh, wow, that's pretty serious. Now, why is that important? There's two reasons as to why that's important. One is sea ice is sort of like the refrigerator of the world. It's bright, it reflects sunlight. So when sunlight comes in, it reflects off and goes back out to space. The Earth doesn't absorb that energy. The thing is that what happens is once you start removing that sea ice, then the underlying surface, the ocean, can absorb a lot more energy. That means things get warmer, and that means more sea ice melts, and that means more energy is absorbed, and more ice can melt. And so that loop is a feedback mechanism. We call it a positive feedback mechanism because it reinforces itself. So we're losing a situation where a lot of energy is reflected back into space. And then the other important thing is that sea ice is a cap on the ocean. While it's 40 below in the air, the water underneath is only about -2 Celsius. With the sea ice sitting on top, it has a hard time expelling that energy into the atmosphere. As we start to lose the sea ice, it's easier for all that energy to come out into the atmosphere and warm the surrounding areas. So that's two very important reasons why sea ice is important. And we'll get back to that later in the presentation. And I just thought I'd throw in a picture of sea ice, because I'm guessing a lot of people haven't been up there, and it was certainly very different for me when I first went up there and checked it out. It's quite an interesting place, an amazing place. It's not nice and smooth like I imagined it to be. I'm standing up here taking a photo looking down up on a pressure ridge. You can see jumbled ice just all askew from when ice flows collide. It's a very interesting place, and I feel quite privileged to have been up there. Now, another item that is an indicator of change is glaciers. And what we see here is the Muir Glacier in Alaska. We see a picture from 1941. Ice came all the way down. 2004, ice has receded a long way. This is typical of the tidewater glaciers in Alaska. So that means the ones that flow down into the water. They have receded a huge amount. Glacier Bay is now much, much bigger than what it used to be. Across the rest of the world, pretty much all glaciers have been receding. There's a couple, maybe 1 or 2 in New Zealand, and one or two in South America that have moved forward a little bit. But other than that, everything else is receding. This image here, this is Jakobshavn Glacier in Greenland. And the backside of this is the ice sheet. And we've got an image here. The solid ice is all the way back here, and the rest of this is just icebergs carving off. It's just that they all mix together, and as they float out, it looks like a white image. This is where the glacier tongue, the solid ice, was back in 1851. And you can see as we go back in time, it has receded further and further back. Now, why is that important? The reason people are concerned about this, especially in places like Greenland and Antarctica, is that they're worried that these glaciers act like corks in a bottle. So you take the cork out, which is the front end of this glacier, and then the ice on the ice sheet, which is actually a plastic substance, over a course of time can ooze out, and we'll lose a lot of volume of ice, and it'll go into the sea, and we'll end up with sea level rise. That's a very long-term process, and actually a lot of the stuff as to how that works and how it could occur is still unknown. We're working on that. We've got some very good people working on it. But in terms of you might have heard all sorts of crazy things in the media about the fact that, well, sea level could go up 1 metre, it could go up 2 metres, who knows. When you hear numbers like that, that's actually due to the dynamics of ice, the dynamics of the ice sheets moving down. It's not all to do with melt. The concern, melt is only one small part of the story. The big concern with sea level rise is actually the fact that ice can move off the shelves, off the ice sheets into the water. And there's a reason that people are concerned, because if we look at global sea level rise from back 1860, 1870 up to the present, we've seen a pretty substantial rise. Now there's two things that contribute to that. One is, as I said, the sea ice, the ice from the glaciers going in. Sea ice plays no role in this. Sea ice is already the water that is in the oceans. It just freezes and thaws. So this is ice from the land going into the ocean. And the other factor is that the planet has warmed, so that means the water has expanded, so thermal expansion. Those two items contribute to this rise that we've seen. And I thought I'd also throw in Northern Hemisphere snow cover. We haven't seen a large change in that. We've seen it being fairly steady, then a bit of a step change, and then again it flattens out. That's just the aerial extent. That doesn't say anything about volume. And assessing volume over the globe is actually quite a tricky proposition, so I'm just going to leave that there and say these are some changes that we've seen. So permafrost. Permafrost has been in the news quite a bit, I know, because I've had a lot of people call me up and ask me about it. We've got all sorts of things going on, from way back in 2001, talking about Arctic adding to global warming. This item here, Canada's permafrost retreats, that's actually just from last month, where areas up near Hudson Bay in Canada, they've found that there used to be permafrost there over the last 50 years and it has now all disappeared. The permafrost line has moved northward. An interesting item from CBC Canada, where Dawson City, which is way up on the Yukon, the famous Klondike Gold Rush, they had to spend a huge amount of money repairing infrastructure because the permafrost thawed and it caused a lot of havoc. So the thing that you might not have a really good grasp on is, what is permafrost? It's something that we don't see a lot of down here. There's a little bit up in the mountains because it's cold enough. But permafrost technically is defined purely by temperature. It's any area that stays below freezing for 2 or more years. And effectively, what happens is that in cold areas, more energy is expelled from the ground than taken up. So you end up with a situation where it's frozen. That's in very simple terms. Where is permafrost? Well, it's where you would expect. It's high up in the high latitudes, Canadian archipelago, from Hudson Bay around, through to the north slope of Alaska, and over to Russia. And we've got a few categories of permafrost, and that is continuous permafrost, and that means that if you went out, poked a hole in the ground, 9 or more times out of 10, you would hit frozen ground. Discontinuous permafrost, this area in the green, and it covers actually a large amount of Alaska, is an area where it's not all frozen. Some of it is, 50 to 90% of it is. And so you might have situations where you've got a south-facing slope or a southerly aspect, something like that. The sun hits it more, and so it's not going to be frozen. Or you've got an area where there's trees shading it and it's going to be frozen. And then you've got other random things, sporadic and isolated. And just like in Colorado, we have isolated permafrost up in the mountains. We're at a high enough altitude. Now, permafrost obviously covers a gradient. It goes from from south to north. And if we look at what it means, if we take a transect through Alaska here, we've got situations where we've got discontinuous permafrost, and it just means that there's remnant bits of permafrost, doesn't go down very deep. The equilibrium between the atmosphere and the geothermal heat flux, the heat that comes from the core of the Earth, is such that you only get a little bit of surface freezing. As you go further north and more energy is expelled from the ground than comes in, you get very deep permafrost. And way up Prudhoe Bay, which is up here, it's at least 600 meters deep. And if you go to places in Russia over here, in deep Siberia, it's well over 1.5 kilometers deep. That's the depth to which it is frozen. Now, a lot of the stuff that I'm going to be talking about is to do with near-surface permafrost. It's a very non-technical term that a few of us just use. There's no strict definition, but what we're talking about is just the upper few meters of permafrost. And that's very important for numerous reasons that I'll get to. That's the area that you live on, you walk on, infrastructure is built on, and vegetation is in. So that's why we're concerned about it. And another item that I wanted to mention is the active layer. So each season in the summer, a portion of the permafrost melts down to a certain level. Depending on where you are, that can be from, say, 1 foot to maybe 8 feet, 9 feet. And that little area, if I go back, so this is the active layer here. That's the portion, that is strictly not permafrost. That is the portion that freezes and thaws each season. And when we go all the way up to Prudhoe Bay, it's about half a meter. And so what we want to see is, well, what's been happening with the permafrost? It's touted as an indicator of what's happening in the world. So let's have a look as to what is going on. And the way we do that is through various measurements. And this was taken last year up north of the Arctic Circle in Alaska, and drilling a core, and then into that core we will put a string of temperature sensors. We did this one in summer 10, 12 years ago. You can see here epoxy resin staff that has got temperature sensors all the way through it. And then just to give you a little idea of what the soil is like, there's always this big tufty bit of moss. Up in the high latitude areas, you can see there's no trees out here. You've got some very small shrubs and a lot of moss. So we've got measurements from around the world, and what does that look like? Well, this is the active layers for various areas, and we've got records that go back from 1990 to the present. Now, if you look at this, there's something that you can see in general is that you largely see an upward trend. That means the active layer is getting deeper. That's not the case everywhere. You've got situations where here you say, wow, it was very deep there and it's come back. This year, wow, it's a lot shallower. You've got situations like this. This is West Dock here, right up near Prudhoe Bay, and you can see that the active layer, you'd start to say that it's gone down. That's all pretty interesting. The active layer is quite important because it has a large impact on whether vegetation can grow in an area or whether you can build infrastructure in that area. And people tend to look at it and say, oh, well, what's happening with it? There's a lot of concern. But sometimes just looking at it, you can miss quite a few interesting points. As I said, this is one I want you to think about is West Dock up here. And if we look at what's happening deeper in the soil, we can see that at 20 meters depth, we've got a situation where we've seen the temperature go up and up. This is a considerable rise. This is at 20 meters depth. That's a long way down. That's a big change in energy. And these are from boreholes, which are quite different from the active layer measurements. So these ones are actually logged manually. We go up, we've got a pipe here. This thing extends down 60 meters, so 180 feet, 150 feet, something like that. And we have very high precision multimeter that can measure resistance very, very accurately. And we drop down into that a very high precision resistance thermometer and take the measurements. This is 10 years ago, and this is a guy, Tom Osterkamp, who was a professor at University of Alaska for many years. So if we look at that same, some of those same places, and we look at what's happening in the temperature profile, you can see again, this is from 20 meters down to 50, and we can see a few of the locations. So this is West Dock, it's way up here. We've got Chandler Shelf, which is a little further down, and we've got Old Man, which again is down here. And so all the way down through Alaska, we see a situation where back in 1993, which is the black square line, temperature was down here. So at West Dock, negative 9.5 degrees Celsius. 2005, wow, where we've increased the temperature at depth over a huge volume of rock and soil. We've increased it by 1 degree. Same story elsewhere. You can see, again, earlier measurements, later measurements. So even though the active layer here has actually gone down a little bit, overall, a huge amount of energy has been absorbed by the ground. And what does that tell us? That tells us that chances are it's actually in the winter that a lot of the warming has occurred. And that is actually quite true when we look at instrumental records. So I'm just saying that what I'm showing here is some data from Alaska, and then halfway across the world in Russia, pretty much the same story. That's Novaya Zemlya, this is the Yamal Peninsula, that's the top end of Scandinavia, Finland, Norway, up there. And again, here we see the same situation, 15 meters depth, we see a large increase in temperature. Here, we've seen a similarly dramatic situation where temperature it's almost at the freezing point. So almost at the point where we're going to thaw a huge amount. And then a few more sporadic situations. The one thing you don't see here is that temperature is going down. So that's a very important thing. This is happening all over the world. And there's a couple of reasons why we're seeing this. One is temperature, and the other one, which I'm going to get to, has to do with snow. So we've seen what's happening, and it's enough to cause us concern. And we want to know, well, what's going to happen in the future? We've seen the trends in temperature going up. We've seen the active layers, for the most part, increasing. We've seen way more energy going into the soil. Temperatures are warming up. What's going to happen? Well, how do we predict the future? Climate models are pretty much the main way that we can attempt to predict the future. I'm going to tell you a little bit about them in a minute. And then part of the climate model is the permafrost model, or you can have a separate one that is not part of the full land, atmosphere, ocean, sea ice system, and you can use that as a nice test compared to the complete model. And we're also going to talk about some climate system interactions that concern us. So what is a climate model? It's a nasty, nasty bit of computer code that basically emulates the physics of all of these processes. In the atmosphere, we've got precipitation, evaporation, we've got clouds forming, we have heat exchange, we have thunderstorms, we have cyclones, we have the dynamics of the atmosphere. That's just the atmosphere. Then we've got the ocean. We've got currents, we've got temperature, we've got salinity changing. We've got to model the fluid dynamics of it moving around the continents. We've also got sea ice. We need to know the rheology, how the various chunks of sea ice move around with the winds and the ocean currents, how they bang into each other, how they come apart, how thick they are. And then we've got land processes, and that's what I work on. And that includes snow cover, vegetation. We want to know how much the plants transpire, how much water they take out of the soil, how much soil moisture is evaporated into the atmosphere. Is it dry? Is it wet? When does the snow run off? How reflective is the snow? All these sorts of items. It's a huge amount of code that goes into this. And we have an understanding of these processes. We understand the physics, and then we translate that into mathematics, and then from there, we translate the mathematics into computer code. And then we put it on a computer and run it forward and see what happens. And we do that sort of in a grid system because that's the most practical method. And this is a little diagram that says, basically you've got grid boxes that have various state properties with them, and the computer calculates, well, how much moisture went into that area, how much went out, how much went up, did precipitation fall out, all these sorts of things. So the large atmosphere, ocean, sea ice, land climate model that I'm talking about, which many of you have probably been up to Boulder and been up to the National Center for Atmospheric Research. That's the group that I work with on this stuff. The model that is being developed, it's over 1.5 million lines of code. And people say, oh, so you made this model. Well, it's me and about 1,000 of my closest friends, maybe more. I only work on one small part of it. Things are way too complex for me to work on every item. I work on the land, I've got friends that work on clouds, aerosols in the atmosphere, all sorts of stuff. The complexity is actually quite amazing. And the fact that it produces a very good answer often astounds me. But this is what my day-to-day looks like. It's not that glamorous. This is just miserable code that I work on. And I go, oh, how can I represent these processes better? How can I make the model look better? And to run a full GCM, full global climate model, for 100 years takes months and months of supercomputer time. They're very complex, they take a lot of time, and we don't treat them lightly. It's a very serious undertaking. So what I'm going to show here, if I get the mouse working, whoa, no. Few technical difficulties. Bummer. No chance of... I'm actually going to pop down and do this because it's a pretty cool animation and it's worth people seeing what a climate model actually is, what it produces. This is just for a January. You're just looking at the cloud system that is produced in an atmosphere. And if I told you this was from a satellite, you would probably believe me. But this is what the model produces. You can see cyclones being produced here. You've got easterly currents here. You've got the big westerlies. You've got the polar vortex down here spinning off. These models are similar, but slightly different to those that are used for numerical weather prediction. The difference is that in numerical weather prediction, we don't worry about quite a number of things because it's only a very short-term process. You're only looking 2 weeks into the future, not 100 years. But well, anyway, I thought that was quite impressive when I saw it. That's the result of millions of lines of code and a lot of time on a computer. And that was just 1 month that I was showing you. So we've got these models. And we want to know what's going to happen in the future. The number one thing that we're concerned about in terms of the future is what happens to the carbon dioxide content of the atmosphere. There are various scenarios. Will we level off at what we have now? Will we keep producing more and more carbon dioxide in the atmosphere? Will it go nuts? This is the result from the IPCC, the Intergovernmental Panel on Climate Change. This is the mean projection for the A1B, the business as usual scenario. So that means we sort of keep putting out carbon dioxide at the same rate we've been doing over the last about 20, 30 years, and then we level off at some point in the future. This is the average temperature change that is seen at 2080 to 2099. And this result is the average of 20 models developed by independent groups across the world. And the reason that everyone tries to stay independent is to make sure that, well, we came up with this result. Does that seem crazy? If another group in, say, England comes up with the same result, we go, maybe it's not crazy. Maybe this is what's going to happen. And this is the average of them all. Some look a little different, but overall, they all have this same pattern. And for me, working in the Arctic, there's something very concerning about this. The colours you see here, talking about a lot of change, all up here in the Arctic. And part of the reason for that is that feedback mechanism that I was talking about, to do with the sea ice. Same thing with the snow. We lose the bright reflective surface, and therefore more heat is absorbed. More heat is released from the ocean than used to be up in this area as well. So that's quite concerning. And what does that mean for permafrost? Well, if we just take the section north of 60 degrees, just the Arctic, the land area, and we have a look at what one particular model, that's the one from NCAR, the institution in Boulder, and we see what's going to happen with that. We go back to 1900 to 2100. This is all model, no data in this. This is what the model produced. And here is what reality is over this period here. And if you take this line that's here, it actually matches up pretty well with the line here. We've got some uncertainty, and that's why we've got the bands. This is actually the average of about 5 or 6 runs together. The thing you see is for various different projections here. We've got the A1B, that's the business as usual. That's the big map that I showed you a second ago. And you can see that temperatures rocket up and then stabilize out. You've got the A2 scenario. This is the aggressive use of fossil fuels. It's going up. It's off the chart. B1, that's a situation where we imagine that we come up with some fantastic technologies and our dependence on fossil fuels goes down. And then most interesting is a situation here. This is called a 20th century stability run. And what we assumed was that at the year 2000, no additional carbon dioxide entered into the atmosphere. And so we stabilized, we left carbon dioxide at what the current rates are. And you can see that, well, it still has a little bit of warming to go. So those are the various scenarios. What does it mean for permafrost? Well, it means something quite concerning. I'm talking about the near surface permafrost here, just the top couple of meters. And that's the stuff that's important to us. There's deeper permafrost, as I showed you before, it goes down hundreds of meters. That stuff is safe. That takes thousands of years to thaw out and took thousands of years to actually develop into that. This is an interesting plot. This is the result from the coupled climate model. We had a situation where at 1980 to 1999, this is where estimated permafrost was, the dark blue, and then what it estimated at the end of this century. And you can see a dramatic reduction. And this is just the area in terms of millions of square kilometres of the area that contains near surface permafrost. You see we've been on a slight downward trend and then it starts to accelerate dramatically as we go further into the future. And even we've got the situation where there was that commitment run, the stability situation, even then things tailed off. And I'll get to that and I'll explain why that happens. But another thing we wanted to do is make sure that, well, is our model correct? Are we doing things properly? Should we have a look at what another model does? And that's what we did. That last image that I showed you caused quite a bit of controversy. People freaked out. I mean, we freaked out when we saw it. We thought, what's going on? We're losing all the upper bits of permafrost. So what we did was we took the meteorology out of the big coupled climate model and forced a different permafrost model. A completely independent, actually a completely different solution method. Very fast model. And what I've got here is a situation where if I use present day information, the current temperatures, this is the simulation I get. I'm going to say don't worry about the colours, it's more just looking at the area. And you can see that we put permafrost in the right places compared to what the observations are. So you'd say, well, I'm pretty happy with this model, it does a good job. So let's take it and let's force it with the scenarios of climate in the future. We've got the A1B scenario, and you see a huge amount of permafrost has disappeared. And that means that what's happened is it started thawing, and it's no longer sustainable. We've got A1B, and then we've got that far more aggressive situation of the A2 case. These are for 2100. This is a situation at 2100, and you can see a little bit of permafrost still left up here, but what these colours tell me, there's no scale here, is that permafrost there is right on the verge of thawing. So this is a good check. It tells us that what we saw in the other model actually was pretty true, the overall big picture. Now, here we have a situation as to, we're going to look at how permafrost thaw progresses. And the interesting thing about this is that there's a very serious nonlinearity. Remember I said the temperature rise in the commitment case didn't go up a lot, but in the commitment case we saw considerable degradation in permafrost. And this is part of the reason as to why. What we've done here is we've taken a model and we've forced it with a constant increase in temperature. And you can see that each year, this is years here, each year we've got a freeze and thaw event, comes down, freezes, thaws, this is the active layer here, we've got permafrost down here. Then it gets quite warm, but we're still increasing temperature at the same rate. And what we have is the development of this thing called a talic. And that's an unfrozen section between the deep permafrost and the active layer. And once one of these things develops, you can see that basically the permafrost takes a hike. It goes south. This is one of the more interesting things, that there's a big nonlinearity in what happens to permafrost. And you can see the energy uptake increases dramatically. So that's one thing that explains why we've seen a dramatic decrease in permafrost in the future. Another thing is, as I said, the sea ice provides a cap on the ocean. When that sea ice is removed, the warm ocean can expel its energy into the atmosphere. That energy can then get pushed over land. And we took some data from a long-term model simulation, and we looked at periods when sea ice dramatically decreased. And we looked at periods where it didn't really decrease dramatically. And what we see is that the temperature increases far more during those periods of rapid sea ice loss compared to situations where there was no loss. So part of the reason for showing this is to say that things don't happen in isolation. There's lots of feedbacks. It's a very complex system. There's all sorts of things going on. And the fact that we've got a lot of warm air coming across, hitting the permafrost, that of course induces more and more thaw. So these are things that could happen in the future, and actually when we saw the dramatic decrease in sea ice extent in 2007, we also saw a dramatic increase in temperatures, particularly in the period of October. And the reason for that is normally you've got sea ice covering things over in October. In the case in 2007, there was no sea ice compared to normal, and there was a huge release of energy. So I've got a situation where permafrost thaws due to temperature change, due to nonlinearity, and there's another instance, there's another item that is actually very important, and that is snow. We're up in the Arctic, there's a lot of snow. This is a plot of temperatures from Ivatuck Hills, whatever, I showed a picture of that earlier. That was where the guy was putting in the thermal probe. And what it shows is the blue line is the air temperature. It's the air temperature, it gets very cold, 40 below, it's quite typical, 68 degrees north above the Arctic Circle. The red line, this line, is the temperature at the ground surface. So it's at the interface between the snow and the ground. The atmosphere, the air, there's still an interface between the air and the snow. As most of you know, snow's sort of lighter and fluffier, it's not a very good conductor of heat. And so the more snow you have, the less cold can get into the ground. The less energy can get out of the ground. So if you put a lot of snow on, and it can be very cold outside, but it's not going to, that cold is not going to penetrate into the ground. And this shows it very, very nicely in the fact that the mean annual air temperature is minus 10 degrees C, whereas the mean annual ground temperature, the surface of the soil, is only 1.43. That's a big difference, and that shows how much of an influence snow can have. So I just put this picture in to show that actually in the Arctic we're not talking about huge amounts of snow for the most part. It's actually usually a couple of feet for a huge amount of the Arctic. There's a couple of mountain areas, but we're not talking the same sort of snow that occurs in the mountains of Colorado. This is very typical snow cover. This is way up on the tundra in Alaska. This is on the haul road that goes from Fairbanks up to Prudhoe Bay. This is April last year. And you can see that the snow actually is quite shallow. But snow is a very good insulator, and even the fact that it's shallow like that means that it does actually stop a lot of cold going into the ground. If you removed all the snow from the world, then you would actually have a rather large increase in the area of permafrost. That might seem a little counterintuitive, but the snow insulates, it doesn't let the cold get into the ground. And what we were doing here actually is, on this camera here, we've got a special filter on the lens. When we take a photo of the snow, we can determine what sort of crystals they are. And there's a big difference between the conductivity of various types of crystals. If you have sugar snow, it doesn't really conduct temperature very well, whereas if you've got hard wind-packed layers, it definitely conducts a lot better. So what's going to happen to snow in the future? Well, when we look at the average over all these climate models, what we see is that precipitation up in the high latitudes increases dramatically. Snowfall also increases dramatically. Now, even though temperature has gone up, it's still below freezing. A lot of people have problems with seeing the fact that there's been a huge climate change in the Arctic, but people still say, oh, look, it's below freezing, it's cold. The fact that it's gone from minus 30 to minus 20 is a huge change, but it's sort of a personal perception that, well, it's still freezing cold, there's no warming. And so if it's still below freezing, any precipitation is going to fall as snow. So we're going to see a large increase in snow. But that's the snowfall. We're not necessarily going to see a large increase in all places in terms of the snow on the ground. It's going to get warmer, so things are going to melt. But in areas that are cold enough, you are going to see an increase. You're going to see an increase in midwinter, but not at the beginning and end of the season. So there's my little schematic here of what's basically going to happen. We've got the current snow regime, which goes from October all the way through to May. And then we've got the future case where you have more snowfall, and during midwinter you get a deeper snowpack, but then because it's warmer, more solar radiation, higher temperatures, you actually get that decrease earlier. And what that means is, in the midwinter, there's better insulation, so it can't take in what cold there is, and in the shoulder seasons, it gets more energy from outside. So we've got a double whammy. We've got the fact that temperatures are going up, and we've got the fact that in winter the insulation is going up, but then on the shoulder seasons we're getting more energy in. So all these factors contribute to the situation where we see a large degradation of permafrost. And actually, if you go back to the slides that I showed almost at the beginning, and we saw these very large increases in temperature, a lot of that is actually due to the fact that in recent times in Alaska, we have actually seen a large increase in snow. We've seen increasing snow depths. So half the warming that you see is actually due to the fact that we've had an increase in snow depth in that area. So that's an interesting thing. You could cherry pick all sorts of items in terms of climate science in order to try and make your point, whether it's warming, whether it's not warming. You always have to give the full story and know what's going on. So it's warmer temperatures and the fact that there's more snow. That's why we've seen a lot of increase in temperatures in the soils in Alaska. Now, why does permafrost matter? Why do you care? It's up there. Does it impact you? Maybe, maybe not. Well, it has impacts on the landscape, and it has impacts to hydrology. There's things that we're concerned about, like infrastructure. You can see a situation here. This is a road that actually was ice-rich permafrost here. It thawed out. The road collapsed. These guys are trying to, I think they're just trying to get across it. They didn't actually cause that to happen. And then changes in vegetation, which I'll show, and the big one that we're quite concerned about is the carbon cycle. So this is a little bit hard to see, maybe. You've got ice lenses in this permafrost. This is a chunk of ground that was taken out of this hole. This is in Alaska, July 1999. You've got Kenji from the University of Alaska here, and he's using a gas-powered jackhammer to get at the permafrost. It's very hard. It's rock-solid stuff. And I took a chunk of that, and I put it on my backpack here, and just let it sit in the open air. And something that you see is that it's got a lot of moisture coming out of it. It's nice and shiny. It's got water all over it. And so the water in these ice lenses then melts out. When that melts out and disappears, you've got a situation where there's subsidence. And that can lead to all sorts of changes in the landscape. Potholes, you've got situations where lakes form all of a sudden, trees fall over. We'll show a little bit of that. This is a situation in Siberia. This is from Larry Smith at UCLA. And what it shows is that we've got images from 1973 and images from 1997. If you look at this area, we'll see, there used to be a lake here. There's no longer a lake here. Used to be a lake, no longer a lake. Same here. And what's happened, and this is way up high in the continuous permafrost zone. So, this is in the discontinuous permafrost zone. So what's happened is, because permafrost is impervious, it's in the earlier cases, it's allowed a lake to form. Runoff has gone into it, a lake has formed. When it's thawed out, it's like pulling the plug out of the bottom of a bathtub. And you've got the situation where these lakes have drained. And from discontinuous permafrost through to the cases of isolated and sporadic permafrost, we've actually seen a decrease in lakes. It's like pulling the plug on all these little bathtubs. But as we go further north into the continuous permafrost zone, what we see is lakes are actually developing. And lakes are developing because we're getting more thaw, more water goes in, the water comes out of the permafrost, we've got ground subsidence, and it forms a lake. That's a pretty interesting situation. Another thing is that the timing of river flow changes quite dramatically. Permafrost is impervious. Water used to just, the snow would melt, water would run off, bang, straight out into the river. Now we've got a situation where high up in the Arctic, we've got this larger active layer. Water can infiltrate into it and sit around. So stream flow or hydrographs start to look quite different. And that can have implications for things such as fish and flushing of water out into the Arctic Ocean, which can have an impact on the sea ice. Infrastructure. It's another very important thing. We've got a situation here where people didn't build very well and they put infrastructure on permafrost that was ice-rich. And it melted away, and you've got a railroad that's a dud, you've got a building here in Siberia that's collapsing, you've got a road that's nice and wobbly. And if you ever get up to Fairbanks and you drive around the roads there, they're quite undulating and you'll get this lopey feeling because in various sections the ice-rich permafrost has melted out and you get a nice rolling road. A lot of the images that you see of these situations aren't actually to do with climate change. All of these images that I'm showing here are to do with very bad engineering, very bad forethought. The reason I show them is because if climate change does happen as we project, then you are going to have this situation. Here we have the Trans-Alaska Pipeline. You can see that what this thing is here, these are thermosiphons, and they're designed to draw energy out of the ground and out into the atmosphere, keep the ground nice and frozen. This is just south of Fairbanks, about a third up from Anchorage north, it's about 1/3 up. And so we're in the discontinuous permafrost zone, and we have thermosiphons on every tower. This is steel, it conducts a lot, gets a lot of energy from the sun, and the fact that the oil running through this pipeline is something like 100 degrees Fahrenheit. So there's a lot of potential for energy to be conducted down and thaw. Thing is once you go further north, you don't have any of these cooling towers, because when the pipeline was built in the 70s, people thought, oh, we're fine, it's rock solid, permafrost, no worries, it's going to be there forever and a day. People are now actually quite concerned. There's talk that the pipeline is actually out of spec. It's a very expensive thing. There's talk of building a pipeline in Canada from the Arctic Ocean down to Edmonton. That's a $19 billion project. That's a lot of money. Actually, a couple of estimates of the amount of money that we're talking billions and billions, tens of billions of dollars in terms of maintaining infrastructure if we start to see the sort of changes that we project for Alaska. So that's a very serious economic concern. Now, vegetation changes. As we melt out permafrost, we've got a situation where the active layer is deeper and vegetation can take hold. It's warmer. The growing season is longer. The tundra that was there, little tundra tussocks, they're freaking out. It's warm, I'm going to migrate north. Not quite, but the shrubs go, oh, this is pretty nice. I'm going to move up north. And we've got a situation here where in 1950, you can see this photo. There's not much shrubbery in this area. 2002, we've definitely started to see a migration of shrubs. Now, why is that important? Well, a couple of things. One is that the albedo, the reflectivity of the Earth, changes. You can see the shrubs, they're much darker. This is the tundra, this is the shrub. A lot more solar radiation is trapped. Insulation, the shrubs provide some shading. That's another thing that's potentially a negative feedback. That means they actually, in summer, might provide some cooling. But then in winter, they trap a lot of snow. You get a deep amount of snow in areas that have shrubs. So therefore, that problem that I mentioned before, where we have high insulation from the snow, that's going to occur. So that's going to aid permafrost degradation. And we've got a situation where shrubs transpire more moisture than tussock tundra, so we change the water balance. The other thing is shrubs need something to grow, and that something that they need is carbon dioxide. So in one way, it's kind of good. Shrubs are growing, drawing down carbon dioxide. That's a good thing if we start to see the sort of increases in carbon dioxide that we've already seen. But the concern we have is what is going to happen to the carbon cycle. I mentioned shrubs take up carbon, but the soil in the high latitudes contains a huge amount of carbon. And what we're worried about is what is going to happen to that. The reason that the soils up there contain a huge amount of carbon is that over the years you had plants grow, they died in the summer, it's freezing cold, they don't decompose, they stay frozen, more soil comes in on top of them, more shrubs come in on top of them, the next season's crop of shrubs, and it just stays there, and it builds up and up and up. We have a large amount of carbon sitting in those soils. And what people are worried about is, now that we're thawing that soil, is that carbon going to become active and come out either as carbon dioxide or as methane? Carbon dioxide, that's a standard measure that people use in terms of global warming, is the amount of carbon dioxide. If we think about it over a 100-year period, the global warming potential of 1 gram of methane is actually 25 times higher than that of carbon dioxide. However, the amounts of methane produced are considerably smaller. But this is something that is a real concern. There's a huge amount of carbon up there. This is actually how we measure the amount of carbon that is going into and out of the soil. We've got a little chamber here, and we've got tubes running in and out of them. They go through a spectral analyzer, and we watch it on the computer and record all that data. How much carbon in the summer is taken up by the plants and when they grow, and then how much is released when they die. This situation over here, this is a case where this is actually on a lake near Fairbanks, Alaska. You can see there's trees in the background. What's happened is vegetation has fallen into the lake, it's decomposed, and it starts to produce methane. This is a situation, it's anaerobic, there's no oxygen, so it produces methane. If you have an aerobic decomposition, you produce CO2. So there's a couple of differences there. But what we're seeing is that a lot of these lakes, methane is bubbling up. And this is a situation where in winter, they found a case where it was bubbling up, and you can see someone here stab the hole where the bubbles were and then put a flame to it, and you get spectacular situation of sort of lighting lake farts. That's what someone calls it. That's quite good. But so how much carbon is stored in these northern soils? Well, there is a huge amount. In the permafrost zones, in the upper 30 centimetres, upper metre, this is in gigatons, 191 gigatons, almost 500 gigatons. And if we go all the way to 3 metres, which is where we think it could actually thaw down to by 2100, we see 1600 gigatons. Now what's a gigaton? Does that mean anything to you? It doesn't really mean much to me. But if we translate this into the equivalent CO2 in the atmosphere, that is about twice as much CO2 as is currently in the atmosphere. So it's a big concern, but it's not something I'm saying, freak out, we're all going to fry. It'll take a long time for this stuff to actually come out and make a difference. And that's one of the big questions that we're working on right now, is what is going to happen to all of this carbon that is in the soil? A plant's going to grow more vigorously and take up a lot of it, or is it just going to come out into the atmosphere and cause a further positive feedback? More thawing happens, more trace gases are released. That means more warming and more thawing. That's a big question. And just to give a big picture about why you would care about this, we've got a situation here where we've got Arctic warming going on. Permafrost warms and thaws. Then we've got a situation where, because it thaws, we've got expanded wetlands. If we've got expanded wetlands, so the situation where we've got lakes and the soil goes all mushy, it's all the water in the soil sort of sits around and it starts to decompose, but in a wet way. We have an efflux of methane and we have more global warming. And that comes back and forms a loop. On the other side, we've got a situation where we have this warming occur, we have microbial activity increases, more nitrogen is produced, shrub growth occurs. Some carbon is taken up, But shrub growth in general, actually, because it's much darker, does tend to lead to more warming. So it's feedbacks like this that are happening up in the Arctic that can cause potential situations to occur all over the globe. So that's why you should care as to what's happening up in the Arctic. Now, I've been through what's happening up in the Arctic. I'm just going to go through a very small bit about what's happening down here in Colorado. This is a nice picture. It's a big storm that happened in March 2003. A friend of mine lived up in Netherlands, and they got 90 inches of snow. It was quite an impressive situation. But what is actually happening with snow in Colorado? Well, the records that we've got the Colorado SNOTEL stations. I've heard a few of you talking about what was going on with the snow, and I'm sure you're quite well aware of all these stations and what they, the data that they provide. And I circled these 4 little stations down here because they're quite close to Trinidad, and I just made this plot a couple of days ago to say, well, actually this year, this area is doing quite well. And the reason it's doing quite well, it's an El Nino year, the storm tracks have come south, and the southern areas of Colorado and northern New Mexico have actually done quite well. The rest of the West actually is suffering pretty badly. But just to show that these 4 stations, yeah, they're doing reasonably well. They're above average. The question is what's happening overall? Well, in places like the Pacific Northwest, where it's a lower altitude situation, we can see that there definitely has been a decline since the 50s in terms of the amount of snow. Colorado is a much higher altitude situation. We don't have this big problem of rain on snow situation. This is a study by David Clow from the USGS, where he looked at the record of all the SNOTEL stations in Colorado from 1980 onwards, and he looked at the day of year that 50% of the snow melt occurs. So if we look at a trajectory of a snowpack here from October through to July, this point here is what we're talking about, the 50% snow melt situation. And this is the day of year that it occurs. And what you can see is a very, very slight trend. I'm not prepared to say that that's significant. I'm not sure that it is actually statistically significant. There's still interannual variability going on, and we haven't yet seen any dramatic decreases in snow. Snow in Colorado, I'm sure most of you are aware far more than me. Colorado tends to be a land of extremes. It's very, very wet years and very dry years in certain places. It's not like it continuously goes along. I mean, you just look at this situation and big spikes all along the way. And that's typical of most of Colorado. And then if we look in the West in general, what's happening in terms of stream flow and snow, well, this is the spring pulse onset. This is the period in the stream flow where you can see that first big pulse of snowmelt happening. And this is from 1948 to 2002, the difference. And you can see in the more coastal areas, the maritime areas, that you do definitely have, you've seen this spring pulse move forward in time. It's got warmer, and it's moved forward. These areas are sensitive to the 0 degree threshold. Colorado, not a lot going on. We're still at a very high altitude, we're continental, we stay nice and cold. And again, this is the 50% portion of annual stream flow. Similar situation pretty much. Again, Colorado, not really having much going on there. So what is projected to happen in the future? This is those IPCC projections that I was talking about before. We've got a situation where, this is North America, the annual temperature increase, December, January, February, June, July, August. What do we see in terms of temperature? Well, it's definitely getting warmer. That's one thing that we can say for sure. We're very confident in that. The thing is, that we're less confident in, is what's actually going to happen to the precipitation. And I've put crosshairs on here, and that's close to Trinidad. It's probably south central Colorado, close enough. Precipitation is quite a tricky one. We actually, Colorado's in this transition zone where above it we're quite confident that it's going to be wetter, and below it it's going to be drier. But where that transition zone actually happens is quite a tricky one. It makes things very difficult to foresee as to what's going to happen. In winter, you expect there's possibility of maybe a little bit more precipitation, and in the summer, probably drier. The thing is this is the number of models out of the 20 that agree. And we can see that there's this transition zone where most of the models say yes, half the models say yes, half the models say no. So Colorado's in a little bit of a pickle because it's quite difficult to work out what's going on. If you lived up in the Pacific Northwest, well, then you pretty much know what's going to happen. Like everyone says, oh yeah, summer, way drier. You're all good. We know it's going to happen. It's going to be a problem. We can plan for it. Colorado, not so much. And that's quite unfortunate. There's a lot of work being done on downscaling this information, trying to make it more specific. There's a lot of work in CU that's being done on that. And I'm peripherally involved in some of that. But it's a situation where it's somewhat too difficult to call as to exactly what's going to happen. Overall, it looks like, well, chances are water resources will go down in Colorado. That's our best guess, but our guess has a huge amount of uncertainty. And just to say that the precipitation regime in Colorado is actually quite different across the state. Here you are down at Trinidad, June, July, August, you've got the high precipitation, convective summer rainfall. Wolf Creek, well, it just rains there all the time. Out over here, we've got very flat precipitation, and Durango, again, a little bit of summer, but much more in the winter. Eastern portions of Colorado, you definitely start to see a summer maximum, and summer is the period that we think that there's a better chance of it actually drying out, and so that's actually not good news for you folks. And lastly, we know that it's going to get warmer, so we're going to see a change in the timing of stream flow. It's going to come sooner than before, simply because it's going to get warmer. That's something we do have confidence in. Why is that an issue? Well, the snowpack actually provides a very nice water store. We don't have anywhere near enough dams to store the amount of water that is in the snowpack in the west, and it trickles out quite nicely over summer and provides us with a much smoother application of our water resources than would otherwise occur. You don't want a situation where it rolls around May 1st, bang, all your water is out in the rivers. You'd have to build a huge number of dams to try and keep that water. So in that respect, this is a situation that we need to think about and be wary of. So just to sum up, the Arctic is warming. There's a lot of indicators of that. I've shown you quite a few. Permafrost is degrading. We can see that in the temperature records. We can see it in the active layer records, and we expect that to continue. The big question is how much and when. There's a lot of debate between myself and various colleagues around the world as to exactly when this will happen. None of us can say for certain exactly the rate and timing of the change, but we do know that as temperatures warm, it is going to start thawing out. And the impacts could be far-reaching. And then a little bit closer to home, Colorado precipitation, it's a transition zone. It makes it very difficult to predict exactly what's going to happen. It's a nasty situation. And the one thing we do know is that warmer temperatures are going to produce an earlier stream flow. And I was going to say some final thoughts, and that is about this whole issue of climate change, because there's been a lot of news about it lately. All sorts of scandals, people are making all sorts of rash statements. And the thing that it's very difficult for people to understand what is actually happening. There's a huge amount of misinformation that is being put out there. And that's the stuff that actually annoys me the most. I'm happy for people to be skeptical. There's a lot of skepticism in my own field. The results I've shown here, people have gone, no, I don't believe it. And we've sat down, we've gone through it, and then we've gone, well, okay, yeah, I think that's what's going to happen. The situation where climate change is now a matter of public opinion as to whether it's going to happen or not. That's quite concerning. I don't have a great solution as to how to get removed from that, and the reason for that is it's a very complex subject. I've been working on this for 15 years. I know the background, this is what I do for my job. So I go in every day and I go, oh, well, what's happening in the world? Who's got a new discovery? What disproves this? Is it cooling in this area? Is it warming over here? Most of you don't have that luxury. You do different work. You do equally important work, but that's not the same as what I do. And it's a very complex subject. You're in a situation where you have to take someone's word for it. It's like me turning up at a mine and going, well, I guess I just start digging, right? And it is, I guess what I want people to take away from this is consider all the information that you have available to you. Make an objective view of information presented to you. Don't take it just because someone with a PhD said something. Try and look for yourself. And that unfortunately takes time. It's very difficult. And I think there I'm going to leave it and take questions. I don't know, can we have some lights? I see someone down here with a hand raised.
So I've heard a lot about all of these positive feedback loops, and in fact I heard another one just today that the seabed of the Arctic Ocean is also thawing out and releasing evidently quite a lot of methane. So, I mean, do you have a good sense of when all of these positive feedback loops are going to take on a life of their own and become irreversible?
No. I would like to say yes, but the answer is no. A lot of those things that you're talking about, the items that I showed here in terms of the trace gas emission, the models that we've built in the last year and are running right now, those are the first ones to actually have those processes built in. So to look forward from that, that's the new and exciting research, a little bit concerning research. The seafloor stuff that you're talking about is actually a different process from this. That's the methane clathrates that are buried deep down in the ocean. And while you might see a few seeps out of that, the chances of that kicking in is actually expected to be quite a ways off compared to the items on land. You're going to see a few seeps for sure, and you might see a situation, but what really freaks people out, it's called the clathrate gun hypothesis, and people think that this is something that happened to actually bring us out of an ice age, where you had a large underwater landslide and it released a huge cloud of methane into the atmosphere and all of a sudden warmed the entire world. Those processes we still don't have a lot of information on. Some of those things we don't even know how they work. We know what clathrates are, we know that where they are to some degree, it's a little bit hard to map them, but then determining the amount of energy that diffuses down in the sea floor, that's a very slow process, and we don't have a really good grasp on that. So unfortunately, no. A lot of the feedbacks on land and the ones that I mentioned here, some of them we've seen some of those come into play, but we've also seen the overall climate system modulate it and negative feedbacks kick in. So there's a question of whether we're actually at this tipping point where things are irreversible. I personally am not convinced that we're yet at a tipping point. I think there's a lot that we can do in order to bring ourselves back, but we're definitely heading towards it. Any other questions?
I'll ask another one then.
Sure.
So you alluded to this in your closing remarks about public opinion on climate change. And in fact, perhaps due to the recent scandal with the researchers out of the UK or whatever the case may be, it has swung back far more strongly towards people being skeptical about it. And, you know, just in daily life, you don't see a tremendous amount of action to curtail our use of fossil fuels and that type of thing. So, I mean, what's it going to take? And I mean, you know, this is just like a purely subjective type of question, you know, but I mean...
Well, the thing about that, and people ask me that question a lot, and this is where I go from scientist that gives you the best information possible as to what is happening and what can happen. That's where I go. I talk about the science. What you're talking about is policy, and that's where I go back to being a private citizen of the world. And my opinion on that is as valid as anyone else in this room. What does it take? I mean, I drove down here in a car. You know, I fly to a conference. I know that's bad. I think it's going to require some overarching governmental action. And hopefully it pushes things more towards a situation where we gain out of that, such as towards renewable energy. The trouble is that it's what we call the tragedy of the commons. If I tell you, say, don't drive your car, it's bad, yet I'm going to drive mine, which is what's somewhat happening on an international level, you're not going to be very happy. And so it takes everyone to kick in and take part in this. And to make sure that everyone kicks in is a very difficult proposition. There's a lot of work on game theory and prisoner's dilemma and all those sorts of things about how that can happen and how the fact that it often does not happen. So what it takes, it's going to take a lot of action, but hopefully it's some sort of positive action where we see a situation where everyone goes, well, I don't need to burn fossil fuels, I'm going to use some renewable resource. Technology has done wonderful things in the past, could help us out in the future. Don't know. It's a big question, and I don't have an answer, sorry. Yeah?
Is there some reason that you know of or you think of that it's only the northern hemisphere that's getting warmer? Because the southern didn't seem to be.
No, I mean, one of the big reasons for that is that the northern hemisphere is, it's the geometry of the continents on the globe. And the southern hemisphere is dominated by ocean. There's little Australia there, that's where I'm from, yay. South America, a little bit of New Zealand, South Africa. But the ocean has a higher heat capacity, and that means that it has to absorb a lot more energy before it changes temperature. So we don't see the big temperature changes that we do in the northern hemisphere, where it's mostly land dominated. And then the configuration of the poles is such that you've got the Antarctic continent sitting right on the pole in the southern hemisphere, and you've got the ocean, the Arctic Ocean, sitting right on the pole in the northern hemisphere. And so we've had that situation of the positive feedback in terms of ice albedo, the reflectivity, and one of the big things is that as we've seen the sea ice retreat, we've seen the ocean expel a huge amount of energy. So that's the main reason as to why you've got the disparity in the north versus the south.
When you see a lot of those apocalyptic scenarios in the movies and stuff, they always reach what would be a tipping point, and then you see, you know, just catastrophe happen. Do you see that, or a more gradual passage to something? Is it possible that those scenarios could, you know, be like instant, you just fell off the fence kind of thing?
I mean, the year 2007 shocked a lot of us. We were definitely not prepared to see that. And that was the year that the sea ice dropped dramatically. And we all like, whoa, we didn't expect to see this. What brought that on? That was an amazing, it was a convergence of many things. We saw winds go in a particular direction, less clouds at one time, more clouds at another time. That sort of thing, I don't really know. I mean, the progression in the models is such that you do have large amounts of interannual variability, and you do see instances like we saw in 2007 where you get these dramatic drops, but then something brings it back, and then it sort of chugs along, and the climate generally moves in a certain pattern. Something I will tell you that is quite concerning is all those scenarios that I showed you make assumptions about emissions. And when they were made, which is actually back in the 90s, China and India were not quite at the industrialized level that they are today. So if we look at the increases in CO2 that are happening, they far outdo any of those scenarios that I showed you. So that's actually quite a concern. I am not prepared to say that we're going to see some sort of massive apocalypse, but if you take it to the end, I mean, you're going to see sea level rise. You're going to see places like Bangladesh, the Maldives, they're going to be inundated. Florida, Miami. Miami, they'll build walls there because that real estate is way too valuable. Bangladesh, done. Those sorts of things, personally, I really don't want to think about them. It's scary. I try and keep nice and objective and stick with the science and say, well, this is our best estimate as to what's going to happen. And I showed you the paths of what's going to happen in terms of temperature. So that's the best.
So the odds of it just flipping out in a week's time or something pretty slim then, you would think.
Yes. I mean, the world's an amazing place. All sorts of crazy things have happened. I mean, if you see the power of a tsunami, you see the power of cyclones, hurricanes. Sometimes the natural world just overawes you, but I'm not putting money on the fact that it's going to be an apocalypse that happens like that. But a lot of that is still unknown. So that's, yeah.
Isn't there quite a little bit that you can learn from the prior ice ages in comparison to what's occurring now as far as time and length, etc.?
Yes and no. People look back in time for that very reason, but the processes that have occurred in the prior ice ages have been quite different from the situation that we have now. The situation that we have now is that we're taking these carbon-rich fossils that have been laid down from pre-Permian, so 200-300 million years prior, and we're putting them back in the atmosphere. That can happen with crustal deformation, but the rate that we've been doing it is probably higher than prior instances. For crusts to move and fold and expose, that sort of thing. The closest thing that could emulate it is massive volcanism. But yes, I mean, we do learn a lot from what has happened in the past. The thing that we always have to, it's like statistics. Extrapolating from a certain case is always difficult. It's like jumping off a building, and as you whiz past the 30th floor, you say, so far, so good. But yeah, that stuff definitely is. I don't do a lot of that myself, so I'm not really in a position to comment too much on that.
Is there a direct correlation to the permafrost and glaciers, like Mendenhall Glacier in Juneau, for example? Is there any kind of...
I mean, there's a correlation in terms of the fact that it's getting warmer, and so you're going to see a thaw in the permafrost, and you'll probably see some recession of the glacier. But in terms of any direct interaction, I'd be skeptical that there's anything that's very direct. It's more of a large-scale thing that affects both of them. And indirect processes. So permafrost might affect the atmosphere, and then that comes and affects the glacier, or vice versa. The glacier recedes, and you have more dark surface exposed, and that in turn heats up. So that's that. So
Does your computer model have anything in it that has precedence in it?
yeah, you mean the orbital mechanics? Yes.
I was wondering because it seemed like at one point both the poles would be in the sun the same amount of time.
Yeah, I mean, the thing about orbital mechanics, though, the mechanisms you're talking about work on timescales 19, 22, 41, and 63,000 years. So we're looking only at 100 years, 200 years, so it's actually not a very big factor. And there hasn't been a huge change in solar flux in the period that we've been looking at. So we do include those items, but they're not really much of a player at all in the period, in the time span that we're looking at. So, okay, well, I guess that's it. And thanks for having me down here, and it's been a pleasure. So.